So far we have talked about the diffraction conditions with no reference to the relative intensity of diffraction peaks. So we have found the Bragg diffraction condition 2d sine theta equals n lambda. If we have theta the incidence angle of incidence, and we have elastic scattering of waves from the crystal, and d is the distance between planes, and we have seen that this diffraction condition is equivalent to the so-called von Laue diffraction condition, which is stating that the diffraction condition is satisfied if the change in the wave vector between the scattered and the incident wave vector is a reciprocal lattice vector. This condition is satisfied, the von Laue diffraction condition. We have seen Ewald construction, which is basically saying by looking at the reciprocal lattice and the k vector, and if we draw a circle around the origin, we find that if the tip of the wave vector lies on touches this circle, then basically delta k will be a reciprocal lattice vector, and Ewald construction tells us for which angles we will see this diffraction condition being satisfied. And then we have talked about the Brillouin zone, which is basically saying that if you have the tip of the wave vector touching the first Brillouin zone or any of the Brillouin zones, you will see constructive interference. So now we want to discuss the diffraction from the crystal lattice with reference to the relative intensity of diffraction peaks. And if you think about what determined the relative intensity of the diffraction peaks, the scattering amplitude has to be proportional to the charge distribution of the scatterer, because as we have discussed initially, the interaction of the X-rays with the atoms is through the electron cloud. So and because we have a periodic structure, a periodic pattern of atoms, the charge distribution, the electron density n as a function of r, the position vector, is basically going to be periodic in the lattice. And furthermore, it has to depend on the phase factor of the scattered wave, since as we have shown, the phase factor determines whether or not we get constructive interference. As you have seen in the Ewald construction, the angle basically determines if you will get a delta k vector, which is a reciprocal lattice vector. So if we concentrate on one unit cell for one building block, we can talk about the scattering amplitude coming from one unit cell. So that's what I'm going to call S sub g, the scattering amplitude from one unit cell, and that is going to be given by integral over the cell, the electron concentration, because it has to be proportional to the electron concentration, and integrated over the volume, e to the minus I g dot r. So we're looking at the reciprocal lattice integral over one cell, the electron concentration. And since the diffraction condition has to be satisfied, that g vector is k prime minus k through the von Laue diffraction condition. So if I have capital N cells, I will add the scattering amplitude from each cell to get the total scattering amplitude f sub g, which is n times the integral over one cell dv n of r e to the minus I g dot r. Now you may be wondering where this comes from. Well, recall that we have Fourier's theorem. Basically, since n of r is a periodic function, it can be written as a sum over the Fourier coefficients ng e to the I g dot r. This is Fourier's theorem, and the Fourier coefficients were given by inverse Fourier transform 1 over the volume of the cell integral over the cell dv n of r e to the minus I g dot r. So the Fourier coefficients, the amplitudes of the sines and cosines basically, multiplied by the volume of the cell, gives me the scattering amplitude. Okay, so the contribution of one cell to the scattering amplitude is integral over the cell dv n of r e to the minus I g dot r, and the total scattering amplitude is basically given by capital N, the number of cell times the scattering amplitude given by one cell. Now, the intensity of the scattered beam is basically proportional to the total scattering amplitude square. So by the way, we call this scattering amplitude coming from one unit cell as the geometrical structure factor, and capital N times the geometrical structure factor gives us the total scattering amplitude, and the intensity of the scattered beam is proportional to the total scattering amplitude absolute square. And where does that come from? Well, if you look at the intensity of electromagnetic waves is basically measured by the amplitude of the amplitude squared of the pointing vector, which is 1 over mu 0 c capital E squared. So the electric field component is related to the magnetic field component. E is equal to BC in an electromagnetic wave, and we have the intensity, the power per area proportional to amplitude of the electric field component square. So that's similar to this. We have this electric field component is related to the electron concentration, and the intensity is given by scattering amplitude, total scattering amplitude squared. Okay, so now we have the concept of the geometrical structure factor, which is giving us the contribution to the scattered intensity from one unit cell. We have the total scattering amplitude F sub g, which is the number of cells times Sg. The geometrical structure factor, on the other hand, is related to the periodic structure of the electron concentration, and it is the volume of the unit cell multiplied by the Fourier coefficients of the electron concentration, and the intensity is determined by absolute value of Fg square, which is the basically telling us that the intensity is determined by total scattering amplitude. Okay, now, so if we have more than one atom in the basis, then we will have a more complicated situation. The electron density at position R will be written as a superposition of the electron concentration of the jth atom, where J runs over the number of atoms in the basis. So here we have a 2-atom basis. So we have one atom at the corner, which is the detector has a position R with respect to this corner atom. The second atom of the basis has a position R sub j with respect to the corner atom, and the second atom has a relative position or the detector has a relative position with respect to the second atom of the basis as rho vector, which is R minus Rj, as you can see from this vector construction. So electron concentration of the J atom with respect to the detector will be determined by n sub j at position rho with respect to the detector, which is n sub j at R minus Rj position. So now if I have not 2 atoms but S atoms in the basis, the electron concentration has to be written as a superposition of the contributions from all atoms. So it will be sum from j equals 1 to s, the number of atoms in the basis, and j of rho. So I have to consider the total electron concentration in the basis with all the contributions from s atoms in the basis. Now, if I look at my geometrical structure factor Sg here, it was the integral over the cell, the electron concentration e to the minus g dot r dv. For electron concentration, I consider the contribution from individual atoms in the basis, sum over j equals 1 to s and j rho. And for rho equals r minus rj, for r I can substitute rho plus rj. So e to the minus ig dot r becomes e to the minus ig dot rho plus rj. So it's the same integral, but now I have transformed from r to rho. You can see that this integral contains e to the minus summation over j equals 1 to s e to the minus g dot rj, which does not belong to this integral because it's just it does not have anything to do with the volume of the cell. So I can take this out of the integral. So sum over j equals 1 to s e to the minus I g dot rj multiplied by the integral over the cell nj of rho e to the minus I g dot rho dv. So this for the jade atom will be an atomic property of the jade atom in the basis. So that's going to be called the atomic form factor. So this is going to be determined by the electron distribution in the jade atom of the basis. So it's the atomic form factor of the jade atom. Then we will have the geometrical structure sum over j equals 1 to s f sub j, the atomic property of the jade atom, atomic form factor multiplied by e to the minus I g dot rj. So g is our reciprocal lattice vector, rj is the position vector of the jade atom of the basis with respect to the corner. And we can write this as xja, yjb, zjc, a, b, and c are our basis vectors in the direct lattice. So this is a dot product between a reciprocal lattice vector and a direct lattice vector, where the direct lattice vector is the position vector of the jade atom of the basis with respect to the corner. So if I write this more explicitly, it will be xj, yj, and zj will be a number between 0 and 1, and g dot rj will be, I write the reciprocal lattice vector ha plus kb plus lc dot product with xja plus yjb plus zjc, and this will give me 2 pi xjh plus yjk plus zjl. And why is that? Because remember, for example, a vector was equal to 2 pi over a dot b cross c multiplied by b cross c. So something like this. And you can see that the dot product will give us xjh, yjk, zjl, etc. So we have to remember this in order to do this calculation. Now, we can summarize this result as the geometrical structure factor for a situation where we have more than one atom in the basis is sum over j equals 1 to s f sub j, the atomic form factor of the jade atom, exponential minus 2 pi I xjh plus yjk plus zjl, where xj, yj, and zj are the position coordinates of the jade atom in the basis with respect to the corner. So this expression gives us the scattering amplitude from HKL planes. So that's what it is telling us. And it's giving the scattering amplitude for one unit cell. So we have to multiply it with the number of unit cells to get the total scattering amplitude. The geometrical structure factor need not be real. It can be, well, as you can see, it can be a complex number. But because we're taking absolute squared of the total scattering amplitude to get our observable, the intensity, it does not create a problem. And if we find that the value of the geometrical structure factor is 0 for a certain HKL plane, this implies that the interference from that plane family will be destructive. So there will be no diffraction peak coming from the scattering from that plane, because there will be intervening planes that will cancel out the diffraction. Okay, so as an exercise, let's calculate the structure factor for the BCC lattice. Okay, the geometrical structure factor for the BCC lattice. Now we start with looking at the BCC lattice as a simple cubic lattice with a basis consisting of two atoms at the corner 0, 0, 0 and at the body center 1 half, 1 half, 1 half. The two atoms are identical, so I'm not talking about a cesium chloride structure. It's a body-centered cubic lattice with one atom in the basis, but I'm considering the BCC lattice as a simple cubic lattice with two atoms in the basis that are identical. So the atomic form factors will be F1 equals F2 equals F. So I write the geometrical structure factor sum j equals 1 to 2, the two atoms in the basis, f sub j e to the minus I g dot rj. So these f values are the same, so there's only one f. For j equals 1, I have 0, 0, 0 position, so exponential minus 2 pi I 0, plus f times exponential minus 2 pi I, so h dot product with 1 over 2, so ha vector dot product with 1 over 2 x hat, etc. So I will find h over 2 plus k over 2 plus l over 2. So this will give me the geometrical structure factor f times 1 plus exponential. The 1 over 2's will get rid of the 2 minus pi I h plus k plus l. So this is just an application of this. So I'm looking at the position vector of the jth atom in the basis and taking the dot product with the g vector. So this is xja plus yjb plus zjc dot product with the reciprocal lattice vector g. So that's this application. Okay, so the position vectors were at 0. So for R1 I had 0 x hat plus 0 y hat plus 0 z hat, and for R2 I had basically the 1 over 2, so it's going to be at position 1 over 2 x hat plus 1 over 2 y hat plus 1 over 2 z hat. So basically this dot product gives me this result. Now I want to look at algebraically what is happening to this geometrical structure factor. So h plus k plus l will be an integer for sure. So basically I have the geometrical structure factor equals atomic form factor 1 plus e to the minus I pi n, and e to the minus I pi n using Euler's formula is cosine pi n minus I sine pi n. Sine pi n is 0, so I obtain f times 1 plus cosine pi n. So what will happen to this geometrical structure factor depends on if n is even or odd. So if n is even, for example cosine 2 pi, that will be 1, the geometrical structure factor will be 1 plus 1f, 2f, so that will correspond to, for example, h equals 1, k equals 1, l equals 0, 1, 1, 0, h plus k plus l is equal to 2, which is an even number, or 2, 0, 0, for example. However, if n is odd, then I will have cosine pi, for example, which is minus 1, and the geometrical structure factor will give me 0. For example, 1, 0, 0 or 1, 1, 1 planes will give me destructive interference. So there will be no diffraction peaks coming from these planes. So those planes whose indices add up to an odd integer will give destructive interference. The physically scattered beam from 1, 0, 0 interferes destructively with an intervening plane. So you can see what is happening in the direct lattice. Here's our 1, 0, 0 plane. Here is the atom at the body center. And basically the intervening plane is the one that is built by the body center atoms, and that will be causing destructive interference from 1, 0, 0 together with the scattered waves from 1, 0, 0 planes. Disregarding the SG is equal to 0 planes, we will get a pattern that looks like a face-centered cubic lattice, because the reciprocal lattice to body-centered cubic lattice in our discussion of Brilliant zones, as we have shown, is a face-centered cubic lattice. Okay, so let's do the same exercise for the face-centered cubic lattice. Now I can think of the face-centered cubic lattice as a simple cubic lattice with 4 atoms in the basis. What would that be? 0, 0, 0, the corner, and then the 3 other atoms in the face centers. So you can think of you can put one atom in the corner, and then you can think about the three planes it has connections with. Those have the atoms at the face centers. So if I calculate the geometrical structure factor, I'm assuming these atoms are identical, so the atomic form factor is F for all of them. It will be 1 that's coming from the first atom at position 0, 0, 0, plus exponential minus 2 pi I k over 2 plus L over 2, second atom, h over 2 plus k over 2, third atom, h over 2 plus L over 2, the fourth atom. So in summary, I find that the geometrical structure factor is F times 1 plus e to the minus I pi k plus L, e to the minus I pi h plus k, e to the minus I pi h plus L. Now I have to see what can happen in this scenario. Now, if h, k, L are all odd, what happens if you add two odd numbers, for example, 1 plus 3, 1 plus 5, etc.? The answer is even. If h, k, L are all even, 2 plus 2, 2 plus 4, etc., they are all even. So if they have the same parity, let's say, h, k, L, same parity, the scenario is that I will obtain an even number, e to the minus I pi n, cosine pi n minus I sine pi n. For this, the second one will be 0, and for cosine pi n, where n is even, I will get 1. The geometrical structure factor will be then 1 plus 1 plus 1 plus 1 for f. So the same parity gives me this scenario. If h, k, L are partially odd or partially even, so if they are not, if they don't have the same parity, for example, h and k are even and L is odd, what happens? So if I look at this situation, the geometrical structure factor will be f times 1 plus e to the minus I pi k plus L, so that will be even plus odd, which will be odd, so that will give me cosine odd number times pi, so for example 1 cosine pi, that will give me a minus 1. And for e to the minus I pi h plus k, that will give me a plus 1 because I have assumed h and k are even, the sum is even. H plus L will be odd, so that will give me a minus 1. So the total answer will be 0. So I will get destructive interference whenever there is a mixed parity in the h, k, L values. For example, 1, 1, 0 plane, h and k are odd, L is even. This will give me destructive interference. If they have the same parity, 1, 1, 1 or 2, 0, 0, etc., these will give constructive interference. So we will observe diffraction peaks from these planes. Now, as the last exercise, I want to demonstrate an important property of this calculation. If we look at the structure factor for the diamond lattice, one way to look at it is basically consider the basis and the lattice separately. So if you already know the geometrical structure factor of the cell, if you multiply that with that of the basis, you will obtain the total geometrical structure factor. Why is that? It's a property of the exponentials. If we multiply them, the exponentials, the powers will add up. So it's just a shortcut. So for example, I can think of the diamond lattice. The underlying lattice is the face-centered cubic lattice. So this is the diamond crystal structure. The underlying lattice is face-centered cubic, for which I have already calculated the geometrical structure factor. There is no F here because I haven't put any atoms here yet, so this is just the lattice. Now I have the basis, two atoms at position 0, 0, 0 and 1, 4, 1, 4, 1, 4. So that's one way to think about the diamond structure. And the structure factor for the basis will be then F times 1 plus 1 is from the corner. The second atom in the basis will give me e to the minus 2 pi I h over 4 plus k over 4 plus L over 4, but the 2's will cancel, so I will obtain h over 2 plus k over 2 plus L over 2. Okay, so the total structure factor will be F times the structure factor of the face-centered cubics, the structure factor of the bases. And the zeros will occur if you have e to the minus I pi h over 2 plus k over 2 plus l over 2 is equal to minus 1. Okay, so let's analyze this situation here. If h, k, l are of mixed parity, we have seen in the previous discussion that the face-centered cubic structure gives us a zero structure factor. So from the FCC underlying lattice, we will obtain 0. If h, k, l are all even, then basically we will see that the face-centered cubic lattice will not give us a 0. So we can look at the situation h over 2 plus k over 2 plus l over 2. If this summation is odd, then you will have in the basis a cosine pi or cosine 3 pi or cosine 5 pi, etc. 1 minus 1 will give us 0. That is coming from the basis. Basis gave us the 0. If the summation is even, however, I will have f times 1 plus, for the basis geometrical factor, 1 plus 1. Cosine 2 pi, cosine 4 pi, etc. So that will give me 2f. And because I will also have a geometrical structure factor 4f for this scenario when they have the same parity, 4f times 2f will give me 8f for the geometrical structure factor. Now, if they are all odd, then h plus k plus l will be odd. And then you will have s is equal to f times 4 coming from the face-centered cubic lattice, and then I will have 1 minus I sine n pi over 2. So sine n pi over 2 will give me plus 1 or minus 1. So this will give me 4f times 1 plus or minus I. So if I look at the intensity, since it's proportional to absolute value of geometrical structure factor square, it's actually Fg is n times s, so intensity is actually proportional to Fg square. Anyway, so this will give me s star times s, so it's 4f squared multiplied with 1 plus I, 1 minus I, so that will give us 32f squared. So this scenario, when h, k, l are all odd, will give me a diffraction peak. So as a final remark, we can say that we could talk about the diamond structure as a simple cubic lattice with 8 atoms in the basis. So that's another way to look at it. So I leave that to you as an exercise. So there are two ways to look at the diamond lattice. We can see the underlying lattice is FCC, and then we can talk about 2 atom bases, or we can see the underlying lattice is simple cubic with an 8 atom basis. Okay, so to summarize, we talked about the geometrical structure factor. Basically, this is the extra information we obtain from this is the relative intensity of diffraction peaks. So far we have only talked about under what conditions we will see a diffraction, but if we look at the behavior of the charge distribution, the periodic behavior of the charge distribution, we can obtain information about the relative intensity of diffraction peaks. And what determines the relative intensity of diffraction peaks? If you look at the Fourier series of the electron concentration, it's basically determined by the Fourier coefficients multiplied by volume of the cell. So that's per cell, our contribution to the scattering amplitude is what we call the geometrical structure factor. It's the integral over the cell of the electron concentration e to the minus I g dot r. The total scattering amplitude, however, is the geometrical structure factor multiplied with the number of cells, and the intensity is determined by the amplitude of the total scattering amplitude, total scattering amplitude squared. Okay, and this is related to the fact that we have a Poynting vector which is determined by amplitude of electric field component squared, for example. Okay, if we have more than one atom in the basis, we can talk about the position of the jth atom in the basis with respect to the detector with the vector rho. And with this analysis, when we write the electron concentration in the basis as a superposition of electron concentrations of the s atoms in the basis, we find that the geometrical structure factor can be written as sum j equals 1 to s fj e to the minus ig dot rj. Rj is the position vector of the jth atom of the basis with respect to the corner atom at 0, 0, 0. And fj is the atomic form factor, which is an integral over the cell of the electron concentration e to the minus I g dot rho. Okay, and we have shown explicitly that if you write this position vector as xja plus yjb plus zjc, the ABC direct lattice basis vectors, dot product with the reciprocal lattice vector, this gives us 2 pi xjh plus yjk plus zjl. So this is the explicit form or calculation we need to do for the scenario where we have a lattice with a basis. So this gives us the scattering amplitude from HKL planes for one cell. If you multiply it with the number of cells, we get the total scattering amplitude, which determines our intensity. And since the intensity is determined by absolute squared of Fg, Sg can also be complex. And if we find that this geometrical structure factor is 0 for a certain HKL plane, that implies that we will have no diffraction peak observed from that plane. We have done this calculation for the BCC lattice, where we consider the BCC lattice as a simple cubic lattice with a 2-atom basis at 0, 0, 0 and 1/2, 1/2, 1/2. And we have found that the condition is, if you look at the sum of HKL values for that plane, if the sum is even, we have constructive interference. If the sum is odd, we have destructive interference. And we have visualized this in the direct lattice. You can see, even using Bragg's diffraction, you would find that if you have an intervening plane right in the middle between two 1, 0, 0 planes, which is the scenario we have in body-centered cubic structure, they will be causing destructive interference and no diffraction peak will be observed from 1, 0, 0 planes. We have looked at the structure factor for the FCC lattice, where we have considered the FCC lattice as a simple cubic lattice with 4 atoms in the basis, 1 at the corner, 3 at the face centers. And there we have found from this calculation that if they have the same parity, if HKL values have the same parity, then there will be constructive interference. If they have mixed parity, there will be destructive interference. And for the diamond lattice, which is a more complicated structure, or for any other lattice, now the situation is we have to talk about an underlying lattice structure, and the basis, we have to assign a basis to that structure to get the crystal structure. For the diamond crystal structure, the underlying lattice structure can be thought of as face-centered cubic with a 2-atom basis at 0, 0, 0 and 1/4, 1/4, 1/4. Now I have to pay attention to the geometrical structure factor of the face-centered cubic lattice and also the geometrical structure factor coming from the basis, and this gives me another important condition. So if HKL had this mixed parity, I already know from the FCC structure that I would get no constructive interference. If they're all even or if they are all odd, then I have to see what happens. If they're all even, I need to look at H over 2 plus K over 2 plus L over 2. If that's odd, I get also a 0 because of the basis. If the summation is even, I get an 8F for the geometrical structure factor. If they're all odd, then I find that the scattering amplitude from one cell, the geometrical structure factor, will be 4F times 1 plus or minus I, which is a complex number. So the intensity will be proportional to amplitude of s squared, so that will give me 32 f squared intensity. So this will give a diffraction peak. And final remark, basically we can think of the diamond structure also as a simple cubic lattice. Now this will require a lot more calculation considering 8 atoms in the basis.